about parsimonious reduction and sharpP-Completeness. Uh, okay, parsimonious reduction is basically a reduction from one problem to another that preserves a number of solutions. So here, the count of the S instances is actually preserved in the transformation or in the reduction. It is basically a bijection, that is a one-to-one correspondence between the solutions of the two problems. Like what this means is that generally in reduction, like if there exists a solution for x in x, that means that y must have at least one solution. So in parsimonious reduction, the extra condition that is imposed is that for every solution of x, there exists a unique solution of y, and vice versa. So that is what is the meaning of preserving the number of solutions. And consequently, if counting the number of solutions to x is hard, then counting the number of solutions to y must be hard as well, because y is at least as hard as x. So, if counting the number of solutions for x is hard, then counting the number of solutions to y must be hard as well. Let's talk about what polynomial time parsimonious reduction is. It is parsimonious reduction, in which the reduction actually can be done in polynomial time. So that is the extra condition of polynomial time, as the name implies. And what are polynomial time counting reductions? Polynomial time counting reductions, they are actually a more general class of reductions for counting problems. So polynomial time counting reductions are the general class, and this polynomial time parsimonious reduction are a more special case of this general class. So, and just like many one reductions help in proving NP completeness, parsimonious reductions help in proving sharpie completeness. So that those were the similarities between NP completeness and sharpie completeness. Uh, so and Yeah, let's see what sharpie complete is. A problem is said to be sharpie complete if, no surprises, if it is in class sharpie, and if it is sharpie hard. This is the exact same definitions we've seen earlier for class C complete. That is, if it is in class C and it is C hard. And what is sharpie hard? What does that mean? Every other problem in sharpie has a Turing reduction or a polynomial time counting reduction to it. Polynomial time counting reduction, we had just seen what it is. It was the general class of reductions for counting problems, and this parsimonious reduction was just a special case, and polynomial time parsimonious reduction. And yeah, uh, So, in some instances, when you're proving sharpie complete, parsimonious reductions are actually used, and in other instances, they use Turing reduction as well. Turing reduction, uh, it was seen in the lecture of Oracle Turing machines. Turing reduces to B if there exists an Oracle Turing machine that is supposed to decide A, and it has an Oracle access to B, with an Oracle access to B. So examples of sharpie complete problems are actually like the corresponding the NP complete versions. Like if we take the counting versions of them, then they actually become sharpie complete problems. And yeah Examples are sharp sat, sharp Hamilton path, and sharp clique. Sharp sat is basically you just count the number of satisfying assignments, and sharp Hamilton path. Hamilton path is actually a path in an undirected or directed graph, where every node is actually visited exactly once. So that is a Hamilton path, and counting the number of such Hamilton paths is the sharp version of the problem, sharp Hamilton path. And sharp clique is actually counting the number of cliques of size k. Uh, so yeah, and let's go to Valiant's theorem. Valiant's theorem is it basically states that computing the permanent of a matrix, even if it's as simple as zero on matrices where the entries are just zeros and ones, is sharpP-Complete. So that was Valiant's theorem, and let's actually study something very useful when it comes to proofs in counting complexity, and that is the notion of cycle covers. Cycle covers are useful reinterpretation of permanent, and vertex cycle cover of a graph, it's also simply called a cycle cover, is basically a set of cycles which are subgraphs of G, and they contain all the vertices of G. The emphasis on all vertices. So this will become more clear with the help of an example. And before we see the example, let's just get these points once, and it'll become more clear with the help of an example. The permutation of non-zero edge labels, they constitute the cycle covers, and the permanent of the matrix is actually the sum of product of edge labels of all cycle covers. So this slide will become much more clear after this example, and this is how the cycle cover problem and the permanent of a matrix correspond to one another, and the cycle cover is just a graphical representation of the same. Cycle covers. Let's actually try to construct a cycle cover. Let's first construct a directed graph from this matrix. The way you do that is basically this is like an adjacency matrix. An edge of weight 2 here would correspond to an edge from 1 to 2 with edge label 2. So this is how this graph is constructed, and what it constitute a cycle cover. An example of a cycle cover would be something like this: 1 to 2, 2 to 3, 3 to 4, and 4 to 1. This is a full cycle cover, and a cycle cover need not be necessarily full. Note that Hamiltonian cycle is also a cycle cover, but cycle covers need not always be full. To demonstrate that, let's basically try picking a permutation in this matrix. So let's try picking values, a permutation like this, and the corresponding cycle cover for this permutation would be 1 to 4, 1 to 4, then 2 to 3, then this is 3 to 2, and this is 4 to 1. So that's how the permanent of a matrix corresponds to the cycle cover. That is that, like, if we take a permutation, so basically if we take a non-zero permutation uh, of the edge labels, the edge labels where the weights are non-zero, if we take a permutation of them, and that will correspond to a cycle cover. And when you take the sum of all such cycle covers, the product of all such cycle covers, we basically get a permanent of a matrix. So this is graphical representation of the permanent and the cycle covers, and this is very useful when it comes to proofs relating to sharpie completeness, and that's how cycle covers are useful. An example of something that would not be a cycle cover would be something like this: 1 to 2, 2 to 3, and let's say 3 to 1. This is a cycle, but it's not a cycle cover because vertex 4 is not covered. So it consists of sets of cycles. It's a subgraph that consists of sets of cycles, and that all the vertices must be visited as well. So that was